Hello everyone. In this lecture I shall discuss the power series solution of differential equations. In the previous lectures we have studied the solution of linear differential equation with constant coefficient and a few variable coefficients, and that variable coefficients are of Euler-Cauchy type, means like this: x square y double dash plus xy dash plus by is equal to rx. And the constant coefficient, these are basically the second order. And as you know, the solution, for getting the solution of this, we are putting y is equal to e to the power lambda x. So the solution will come in this form. And here in Euler-Cauchy equation, we are putting y is equal to x to the power n. Okay, so the solution is of this form. Now during complex conjugate, we are getting sin ax cos ax like that. So the solution involves such type of functions. But there are many differential equations with particularly the variable coefficients which do not permit such solutions. Okay, we are not able to get the solutions by the previous knowledge. In that case, we use the power series solutions, right? We use the power series solution. And one more thing, this series must be convergent. Okay, the series must converge to a function, right? And we should discuss the power series solution to overcome this solution. So while we tell about a power series, for example, if suppose I say e to the power x, right, this is a function, and this power series, you know, the Taylor series expansion of this is 1 plus x square by factorial 2, so on, x cube by factorial 3, is not it? You see, it is an infinite series here. It is an infinite series here, or we can write it summation of x to the power n by factorial n is equal to here 0 to infinity. You see, this is an infinite series. So once we talk about an infinite series, then this series must converge to a function. Okay, such type of solution we will consider. If it will not converge to a function, then the solution is useless. Okay, so now while we talk about an infinite series, we have to define a region here, and in this case the region is x mod less than infinity. Okay, means for any value of x it will converge. Similarly, while we write a power series, suppose we write a power series solution a n x minus x0 to the power n, means we must have a region here. We must have a region like this, what we call the circle of convergence. The center is at 0. The center is at x0. Right? The center is at x0. Because I write this is as the center. Center is that x0. And the convergence here. And the radius here is say here r say. Okay. So means while we write a series, and we must specify a region. Within this region, the series will converge. Okay. So a power series is followed by a radius of convergence and a circle of convergence. And if you open this series, the series will take the infinite form as a0 plus a1 into x minus x0 plus a2 into x minus x0 square, so on. So it will extend like this. Okay. So while we talk about this, we should also discuss this x minus x0 mod less than r. This r is called the radius of convergence and x0 is the center. Now once, and in this series what we see, e to the power x. In e to the power x we see that x minus 0 mod is less than infinity, means the center is 0 and the infinite circle of infinite radius, means there is no restriction on x here. Okay, so these are the issues for further analysis, but we simply talk about the solution here. And moreover, during this process of the solutions, we introduce some special functions, okay, called the legendary function and the Bessel's functions. Okay, and subsequently we will have the legendary differential equation and the Bessel's differential equation. So this will come in this process of solving the power series solution. So before the details of our discussion, let me to introduce myself, Professor Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, Burla, Odisha, India. Okay, so without much delay, let us now discuss the details of the solution. So now you are asked to solve find the power series solution of y dash minus y is equal to 0. Basically, the power series what we are solving, the standard form is p0x y double dash plus p1x y dash plus p2x y is equal to, you say somewhere, qx. Okay. So now this coefficient of this should not 0 for any choice of x. This is the restriction here. Means if we divide it, so that means my y double dash plus p1x by p0x, okay, y dash plus I write simply p2 by p0 y is equal to q by p0. So this p0x, we should choose x such that p0x is not equal to 0. Okay, so that x will be your center. This x is equal to your x0, say, is the center. Means this x minus x0 mode less than r. So this is your center. Okay, so we should see, we'll choose the center in such a way, and this will lead you to your ordinary point. Okay, ordinary point. Subsequently, I will tell you the details of this. So here you see, here the coefficient is a constant here. So there is no bar on x. If there is no bar on x, if 0 is the center allowed, then we should prefer 0. Okay, we should prefer 0. So what is the solution here? So I say, consider solution, consider y dash minus y is equal to 0. So let your y is equal to summation of an x to the power n is equal to 0 to infinity. That means here a0 plus a1x plus a2x square plus a3x cube plus so on. Okay, be the power series solution. Let it be my equation 1, let it be my equation 2. Be the power series solution of equation 1. Okay, you see, so I take x to the power n instead x minus x0 to the power n, because at x is equal to 0, this p0 is not equal to 0. So x is equal to 0 is a ordinary point here. Okay, we don't bother about this. So this is the solution. Okay, like in previous case, we choose y is equal to x to the power m or e to the power mx, like that. So this is my solution here. Then my interest is to find what is a0, what is a1, what is a2, what is a3, so on. Now it is a first order differential equation. Okay, so its general solution will involve only one arbitrary constant, is not it? This general solution will involve one arbitrary constant, right? So we see, so now once y is equal to this, we need what is my y dash. So that means my y dash is summation of, here an constant remains silent, n into x to the power n minus 1. The derivative of x to the power n is this. Okay, or if I directly find from this, then derivative of a0 is 0, it is simply a1, derivative of x is 1, plus here 2a2x, derivative of x square is 2x, 2a2x, plus derivative of x cube is 3x square, 3a3x square, plus so on. Okay, now we will substitute the value of y and y dash. We substitute y and we substitute y dash in your equation number 1. Okay, now equation 1 follows. Equation 1 follows. Here in place of y dash, we write a1 plus 2a2x plus 3a3x square plus so on. This is my y dash, minus your y will be a0 plus a1x plus a2x square. Okay, so on is equal to 0. Since this is up to x square, I write this up to x square. Okay, so now I collect the like power of x, means I collect the constant term, I collect the coefficient of x, I collect the coefficient of x square, so on. So that means my a1 minus a0 plus 2a2 minus a1 x plus 3a3 minus a2 x square so on is equal to 0. In the right hand side, can I not write it? 0 plus 0x plus 0x square. Can I not write like this? So now I can compare. So this is my 0, this is my 0 and this is my 0. Okay. So this implies I have a1 minus a0 is equal to 0, 2a2 minus a1 is equal to 0, 3a3 minus a2 is equal to 0 and so on. It will continue like this. Okay. So now you simplify it. If you simplify it, this implies here a1 is a0. As I have already told you, this is a first order differential equation. The arbitrary constant, there will be only one arbitrary constant. So that constant will be, say here a0, rest will be expressed in terms of a0. Okay. So what will be your a2? a2 will be a1 divided by 2. Now you substitute the value of a1 as a0. So this is here a0 by 2, or I can write it factorial 2 to get a pattern. So now, and this implies what happens to my a3? a3 will be my a2 by 3. Now substituting the value of a2 here, it will be a0 by 3 into 2 means 6, means I can write a0 by factorial 3 to get a pattern and so on. Okay, and so on I can write and so on. Now I substitute all this. Actually equation 2 is my solution, so I substitute these values in equation 2 get my final solution. So now equation 2 follows. Now equation 2 follows. Here y is equal to a0 is a0 and here a1 is here a0, a1x, a2 is here a0 by factorial 2x square and a3 is here a0 by factorial 3x cube, so on. So this is equal to taking a0 common. Okay, this is 1 plus x square by factorial 2 plus x cube by factorial 3. Okay, so now this is my answer. Okay, which is the desired power series solution of equation 1. Okay, so this is my answer. Now if I see, is it not the expansion of e to the power x? So can I not write it? It is a0 e to the power x. So is it not my answer? That means while we write a power series solution here, the series must converge to a function. We don't bother about the function. We just leave here. We leave here that this is the answer. But if you see, if you solve it by direct solution by direct method, if I solve by direct method, here y dash minus y is equal to 0, y dash minus y is equal to 0. So by simply variable separation method, so that means my dy by dx is equal to here y, right? So that means here dy by y is equal to here dx. If you integrate it, so that means here log y is x plus ln c. Okay, so now bringing this to this side implies ln y by c is x, removing here ln y by c is equal to e to the power x, bringing c to this side. So that means here y is equal to c e to the power x. If I take c is equal to a0, this is a0 e to the power x. So is it not the same solution we are getting? Now in other method, alternatively, if I have my y dash minus y is equal to 0, put y is equal to e to the power lambda x. The auxiliary equation becomes, okay, it is lambda minus 1 is equal to 0. So that means here lambda is equal to here 1. So therefore y is c e to the power 1x. Okay, if I write this c is equal to a0, I write a0 e to the power x. Is it not my solution? So by variable separation method I am getting a solution. Okay, by constant coefficient technique, considering the auxiliary equation, I am getting a solution, and by power series solution also I am getting the same solution. So what is the advantage of using this power series solution? The power series solution, the advantage is, if this method will not work, when direct method will not work, okay, when direct method will not work, we use power series solution. Okay, so this is the advantage of using power series solutions in solving the differential equations. So the technique of solving this differential equation is now clear. So let me tell you some general process as the ordinary point. Like that, let me to tell you some basic process and solve further examples. Let me to tell you some standard power series. E to the power x is 1 plus x square by factorial 2, x cube by factorial 3, so on. This is, I can write summation of x to the power n by factorial n is equal to 0 to infinity, and x mod is less than here infinity. And similarly, if I write e to the power minus x, it will be 1 minus x plus x square by factorial 2 minus x cube by factorial 3, so on. And accordingly, you write summation of minus 1 to the power n x to the power n by factorial n, x mod less than infinity. So here sin x you must be knowing, x minus x cube by factorial 3 plus x5 by factorial 5 minus so on. It is summation of minus 1 to the power n x to the power 2n plus 1 by factorial 2n plus 1. So this is also valid for all x. So x mod less than infinity. Similarly, your cos x is 1 minus x square by factorial 2 plus x fourth by factorial 4 minus so on. In general, it is minus 1 to the power n x to the power 2m by factorial 2m with x mod less than infinity. Then here suppose write 1 by 1 minus x. You know the binomial expansion. It is 1 plus x square plus x cube plus so on. So this is simply summation n is equal to 0 to infinity x to the power n. Here x mod less than 1 means the radius of convergence is 1 here. It will valid in a circle of convergence with center 0 and radius 1. Okay. Similarly, 1 by 1 plus x, it will be 1 minus x plus x square minus x cube so on. So it will be summation of minus 1 to the power n x to the power n with x mod less than 1. So these are some standard power series. Okay. So now let me to tell you the general procedure for your power series solution. So suppose we consider a second order homogeneous linear differential equation, right? So now it is p0x y double dash plus p1x y dash plus p2x y is equal to 0. Now if I divide this, okay, so that means my y double dash plus p1x by p0x y dash plus p2x by p0x y is equal to 0. And you see here, since this p0x in the denominator, we must have p0a is not equal to 0 for x is equal to a. Then this a is called your ordinary point. A is your ordinary point. And if a is a ordinary point, then we can choose a as a center. Means the power series solution will be an x minus a to the power n is the power series solution. Now if a is equal to 0, okay, then the power series solution is y is equal to summation an x to the power n, okay, is the power series solution. So definitely this is better only when this 0 is the power series, 0 is the center. Okay, so in that line let me write, suppose this is my px and this is my qx. I write it, suppose y double dash plus my pxy dash plus qxy is equal to 0. Okay, so now I say the definition of the ordinary point. Come to a definition. A point x is equal to 0 is said to be an ordinary point. Let it be my equation star say. Said to be an ordinary point of equation star if both px and qx are analytic. Analytic means at the present moment I should say defined. Okay, and the further it is also called differentiable, but we stick to defined here. Are analytic, px and qx are analytic at x is equal to 0. At x is equal to 0. That means P0 is not equal to 0. Is not it? P00 is not equal to 0. So if x is equal to 0 is an ordinary point of star, then the power series solution of star becomes y is equal to summation of an x to the power n is equal to 0 to infinity. So I can write it a0 plus a1x plus a2x square, so on. And be sure that while I write this infinite series, I must write the domain. I must write the region of convergence here. So 0 is the center. Obviously x minus 0 mode is less than r. So what does it mean? We have a circle with center at 0 and radius of convergence is r. Okay. So this is a point of discussion for further analysis of convergence. Okay. So now in view of this, we will find the power series solution. If my y is this, if I want to find the derivative of y, what is y dash? Derivative of x to the power n is n into x to the power n minus 1, n into x to the power n minus 1. So you see here, if I put n is equal to 0, then it's 0. So I write n is equal to 1 to infinity. However, if I write 0, then also no issue. Then if I want to find y double dash, then it will be my derivative of x to the power n. It will again n into here x to the power n minus 1, n minus 1, x to the power n minus 2, in that way. But if you put n is equal to 0, it will 0, n is equal to 1, it will 0, n is equal to 2 to infinity. However, if I write 0, no issue. Okay, we are writing 0 plus 0. So in that way, we find these values and substitute in the given differential equation and find the coefficients, and we see how many arbitrary constants are need to be there in the solution. It should be equal to the order of the equation. If x is equal to 0, is not an ordinary point, then we take then say try for x is equal to 1, x is equal to 1, x is equal to 2. We try it. If x is equal to 1 is an ordinary point, if x is equal to 1 is an ordinary point, then the power series solution becomes y is equal to summation of an x minus 1 to the power n. Okay, and we write it is a0 plus a1 into x minus 1 plus a2 into x minus 1 whole square. So it will be like this. This x minus 1 will be continued in that way. It shouldn't be disturbed. Okay, we will see accordingly. Coming to another definition, regular singular point. I say x is equal to 0 is a regular singular point of equation star if x minus 0 into px and x minus 0 whole square into qx both are analytic at x is equal to 0. Right, both are analytic at x is equal to 0. Instead, if x is equal to a, then I write x minus a into px and x minus a whole square into qx. Both are analytic. Right, at x is equal to a. Means if it fails, if ordinary singular point fails, okay, when ordinary point fails, then we talk about the regular singular point, and this method will lead you to Frobenius method. Okay, and this is not the discussion point at this time. So let us now solve more examples on this. Suppose one more question, you are asked to find the power series solution of this. You see, the previous method will fail. Okay, but we see the coefficient of y double dash is here 1. So not undoubtedly we can say here x is equal to 0 is an ordinary point of equation 1. Thus y is equal to summation an x to the power n is equal to 0 to infinity. That means a0 plus a1x plus a2x square plus a3x cube plus dot dot dot. Okay, let it be equation 2 is a power series solution of 1. Okay, so now we find y dash. So you may write in this implicit form or you may write in this explicit form, but the tragedy is that if first few coefficients are 0, then it is difficult by this method. So let me to try by this series technique itself. Okay, so that means what is my y dash? I need y dash is summation n x to the power n minus 1, and my y double dash is summation n into n minus 1 x to the power n minus 2. Here n is equal to 2 to infinity. Now I substitute all this thing here in equation number 1. Now 1 follows. Now equation 1 follows summation of n into n minus 1 x to the power n minus 2 n is equal to 2 to infinity plus x square into summation of n is equal to 0 to infinity an x to the power n. Okay, so this is equal to 0. If I want to open it, okay, then it is my 2 into 1 a2 plus 3 into 2 a3x plus so on. Here if I want to take the coefficient of x to the power n, then it will be n is replaced by n plus 2. It is n plus 2 into n plus 1, is not it? an plus 2 plus so on this. Then for this term we have, I can multiply 1x square, so it is x square. If I open it, a0 plus a1x plus a2x square plus a3x cube plus so on is equal to 0. Now I collect the like power of x. Okay, here a2 is a constant, here there is no constant here, so a2 is 0. There is not any coefficient of x here, but the coefficient of x is a3, so a3 is 0 in this process. So this implies it is my 2a2 plus it is my 6a3x. There is no term here with these coefficients. Okay, so if I continue like this, it will be my coming to this n plus 2 into n plus 1 an plus 2. Okay, plus here it will be an x to the power n, is not it? An x to the power n. So an whole into x to the power n, okay, is equal to 0. You see, so the advantage of writing this in series form, okay, means if first few terms are zeros, then also we are in safe side, because we are getting this. Here we see this is 0 and this is 0. So equating the coefficients, collecting the coefficient of various like powers of x, we get here a2 is 0, because here it is 0, a2 is equal to 0, a3 is equal to 0, right? But if we collect the coefficient of m, what we are getting? We are getting here n plus 2 into n plus 1 an plus 2 plus an is equal to here 0, and n is greater than is equal to 2 here. Okay, one more correction is needed here. You see here this corrections here. You see, if we go on continuing like this, it will be plus a n minus 2 x to the power n minus 2 plus so on. Okay, now this will 0. You see x square is already there, so x square will be multiplied with this will give you the power n. So this must be here x to the power, this must be here a n minus 2, this must be here a n minus 2. Okay, so this is my a n minus 2. That's why I write n greater than is equal to 2, otherwise this will be negative. So this implies what is here a n plus 2, a n plus 2 will be minus of a n minus 2 divided by n plus 1 into n plus 2 with n greater than is equal to 2. If n is not greater than is equal to 2, then this will be a minus 1, a minus 2 like that. But we are concentrating on the positive index. Okay, so for n is equal to 2, what I am getting? For n is equal to 2, what I am getting? My a4 is equal to, okay, minus of a2 divided by, it is 3 into 4. For n is equal to 2, it is my a greater than n is equal to 2, it is my a0. So a0, so this is minus a0 by 12. Accordingly, for n is equal to 3, I am getting a5 is minus a1 by 4 into 5. Okay, so this is minus a1 by 45 like that, 20. And accordingly, for n is equal to 4, I am getting my a6 is minus of a2 by 5 into 6, but a2 is already 0, we got it, a2 is already 0, so this is equal to 0. In that way I collect the solution here. So for m is equal to 5, here a7 will be minus a3 by 6 into 7 is equal to 0. Okay, for m is equal to 6, here a8 will be minus a4 by 7 into 8, a4 is here minus a0 by this. Okay, so I substitute it, I get a0 by 3 into 4 into 7 into 8. Okay, and accordingly I will get it. So if I write in this way, if I write in the explicit way, then I cannot move up to a8. Okay, I cannot get a perfect answer. So if the first few coefficients are 0, you should move like this. So therefore equation 2 follows. Hence equation 2 follows. This is my solution. Here y is equal to a0 plus a1x. Then next is my a4 exports minus a0 by 3 into 4 export minus a1 by 4 into 5 x5. Okay, and plus accordingly I will write, and if I collect, so a0 term I will collect and a1 term I will collect. So this is equal to a0 term I collect, it is 1 minus x4 by 3 into 4 plus on, and my a1 into it will be x minus x5 by 4 into 5 ... You see, originally the order of the equation was 2, so there must be 2 arbitrary constants. So the general solution must be c1y1 plus c2y2. Okay, so we are getting like that, a0 into y1, right? So this is of the form a0 y1 plus a1 y2, because 2 constants we need to get the general solution. Okay, let me to conclude with one more example. So you are asked to solve this. Okay, previous method will also not work. This is of course an initial value problem. So you see here, except x is equal to plus minus 1, except x is equal to plus and minus 1, all point, let it my equation 1, are ordinary point of 1. Let x is equal to 0 be an ordinary point. So the power series solution is y is equal to a0, or I write it in series form, summation of an x to the power n. Okay, if I write it, I open it, a0 plus a1x plus a2x square, so on. It is n is equal to 0 to infinity. So now this implies my y dash will be summation of an x to the power n minus 1. Writing n is equal to 0, it becomes 0, so n is equal to 1 to infinity. Or if I open it, or if I directly differentiate it, it is a1 plus 2a2x plus 3a3x square plus like that. Okay, Then coming to my y double dash, it is summation of n is equal to, it is n into n minus 1 an x to the power n minus 2. So n is equal to 0 and 1 is useless, so n is equal to 2 to infinity. So if I open it accordingly, I can open it or I write it. So the derivative of this, it is simply 2a2 plus 6a3x, like that. Okay, so now the initial condition at this moment also we can put it, right? Or at last you can put y0 is equal to 1. What does it mean? y0 is equal to 1. You see, y0 is equal to 1. What does it mean? It means when this is 1, it means y is 1, x is 0. So what does it mean? Here y is 1, x is 0. So a0 is equal to 1. a0 is equal to 1. Next is here y dash 0 is equal to 1. What does it mean? It means y dash is equal to 1, x is equal to 0. So if you substitute this here, what you are getting? 1 is equal to, it is a1 plus 0 plus 0 plus 0. So this, from this initial condition we get it. We can get it from the beginning, or at last after getting the final solution we can also get it. Now we substitute all this thing in equation number 1. Okay, so this is my solution, this is my equation number 2, and the given question is my equation number 1. Now substituting all this thing in 1. Now 1 follows. Now I substitute the value of this y dash, y double dash and y. I will get it. Now I multiply 1, then I multiply x square and I collect. So that means if I multiply 1, summation n is equal to 2 to infinity n into n minus 1 n x to the power n minus 2, and if I multiply x square, then it becomes x to the power n minus summation of n into n minus 1 n x to the power n. Okay, n is equal to 2 to infinity, and accordingly if I multiply this, it will be also x to the power n minus 2i summation n is equal to 1 to infinity n x to the power n plus 2 summation of n x to the power n. You see, I collect this x to the power n together. So now I see, this is the power of x to the power n, this is power of x to the power n, this is power of x to the power n. If I want to make it the power x to the power n, I need to replace n by here n plus 2. Then what I will get? Then this will converted to n plus 2 is equal to 2, means n is equal to 0, n is equal to 0 to infinity, n plus 2 into n plus 1 an plus 2 x to the power n. Okay, so now this term is converted to this term, and I collect this term together, okay, collect this term together. So I am getting, and one more thing you can see, you see also here n is equal to 0. So here also if I write n is equal to 0, then no harm, because 0 plus 0 then 0, then okay, here also if I write n is equal to 0, no harm, because putting n is equal to 0, this term itself is 0. So all are in n is equal to 0 to infinity. Okay, so if I collect it, the coefficient of x to the power n, it is n plus 2 into n plus 1 an plus 2, then from the remaining term. So if I simplify it now, so it will be my, so now if I collect the coefficient of x to the power n, okay, I am getting this thing I am getting. So that means my this is equal to 0. So if I simplify it, it is n plus 2 into n plus 1 an plus 2 is equal to here m square plus m minus 2 am. So what is here n, this is n. So this is my an plus 2, and I can factorize it. It will give me n plus 2 into n minus 1 divided by n plus 2 into n plus 1 an. Okay, so that is equal to here n plus 2 cancelled, n minus 1 by n plus 1 an. So this is my an plus 2, and n there is no restriction, n is greater than equal to 0, so that I can find a0, a1, a2 like that. For n is equal to 0, what I am getting here, a2 is equal to minus a0. For n is equal to 1, what I am getting here, a3 is equal to here 0. Okay, From the initial condition, I already get a0 equal to a1 equal to 1. a0 equal to a1 is equal to 1. Already I get e1 from the initial conditions. So accordingly, for an is equal to 2, 3, 4, etc. if I substitute, I will get a4 is equal to 1 by 2 a2, a5, this is here 1 by 3 because a2 is here minus a0, a0 is my minus 1. Okay, then similarly find a5 is 2 by 3, a2 is equal to 0, a6 I will be getting 3 by 5, a4 is my minus 1 by 5. Okay, this is minus 1 by 5 and so on. Now we substitute this, therefore the general solution is y is equal to 1 plus x minus x square minus 1 by 3 x 4, so on. So this is my answer. So now at this juncture my instruction to all of you is that, right, you may write the answer in series form or you may write it in open form. Okay, and accordingly you should simplify. Finally you may substitute the initial condition or at the beginning you substitute. Okay, this is up to you. So here example 3 we solved. Now coming to one more example, example 4. Use power series method to solve y double dash plus y is equal to 0, y0 is equal to 0 and y dash 0 is equal to 1. Okay, so here solution x is equal to 0 is an ordinary point. Okay, so y is equal to summation of an x to the power n is a0 plus a1x plus a2x square plus a3x cube plus dot 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 be a power series solution of equation 1. Let be my equation 1 and this is my equation 2, and accordingly I find y dash is summation an x to the power n minus 1, n is equal to 1 to infinity. If I open it, a1 plus 2a2x plus 3a3x square plus dot 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 dot, and accordingly I find y double dash summation of n into n minus 1 an x to the power n minus 2, n is equal to 2 to infinity, or if I open it, it is 2a2 plus 6a3x plus dot dot dot. At this juncture I should substitute this initial condition y0 is equal to 0. If we substitute it here, I am getting a0 is equal to 0, a0 is equal to 0, and if I substitute y dash 0 is equal to 1, y dash 0 is equal to 1, if I substitute I am getting a1 is equal to 1. Okay, a1 is equal to 1. So initial condition I substitute here, it will be easy. Okay, then I go on continuing and I substitute these things in equation 1. Now equation 1 follows. Okay, I substitute this and I simplify. I will get a0 is equal to a2 is equal to a4 is equal to 0, and my a3 will be minus 1 by 3 factorial, a5 will be minus 1 by 5 factorial, and so on. Okay, so therefore my y will be x minus x cube by factorial 3 plus x5 by factorial 5 and dot 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 dot. So that means my y is equal to simply here sin x. Okay, so this is the answer. You can also solve it by this previous technique, but here it is asked solve it by power series method. If it is not asked, you see what is the answer here. Your lambda square plus 1 is equal to 0. So lambda is equal to plus and minus I. Y is equal to c1 cos x plus c2 sin x. If I substitute these conditions, I will be getting c1 is equal to 0 and c2 is equal to 1. So therefore my y is equal to sin x is the answer. Okay, y is equal to sin x is the answer by previous technique, but here it is asked to solve by the power series method. Okay, so let me to tell more about the radius of convergence to conclude this lecture. Now coming to the more about the radius of convergence, if summation an x minus x0 to the power n be a power series, then the radius of convergence r is given by r is equal to limit n tends to infinity an by an plus 1 factorial, where this an is this coefficient. Okay, and alternatively another, if in terms of the power we can have alternatively one r is limit n tends to infinity nth root of an mod. Okay, nth root of an mode, right? So in both the cases we conclude that radius of convergence cannot be negative. Radius of convergence is always greater than equal to 0, right? Radius of convergence cannot negative, right? Cannot be negative because you are taking the mode. One more thing, not involve I, complex number, because you are taking the magnitude, because a plus ib, the magnitude you are taking, it is a square plus b square root over. Okay, so the radius of convergence cannot be negative, it cannot involve any complex number since we are taking the modulus. Okay, so now let me to solve some examples. Convergence, you see this power is n and this is an. Okay, if this power is 2n, right, then we should take it r square as the formula. Now coming to some examples here. Okay, so solution of I. So here let my am is equal to 1 by 2m factorial, right? So this implies am plus 1 will be 1 by 2m 2 into m plus 1 factorial, means 1 by 2m plus 2 factorial. Okay, so now since this power is x to the power 2m, I should write r square is equal to limit m tends to infinity, okay, am by am plus 1 magnitude, and accordingly I will simplify it. Limit m tends to infinity, am is here 1 by 2m factorial, and it is reversely multiplied 2m plus 2 into 2m plus 1 into 2m factorial. Okay, modulus. Now this 2m factorial cancelled, there is no negative sign, so modulus has no role, so now it is infinity. So r is equal to also root over of infinity is equal to infinity. So therefore radius of convergence is infinity in example 1. If we think of the radius of convergence here, what is your am here? Am is minus 1 to the power m by 2 to the power m. Rather we have to apply the formula of r square, because it is x to the power 2m. So it is x to the power m whole square. So r square is limit m tends to infinity am plus 1 by am magnitude. So this I will be getting 2, and r is equal to a root 2 I will be getting. Okay, in 2i. And coming to this also, what will be the radius of convergence of this 3? Okay, so this is power 2m. So this will be simply 3 by 2 root over. This r is here. Now here in this case, in case IV, this x minus 1 is as if we are not going to disturb it. Okay, in case of 3, in case of 4, so here 1 by here am is I can write it, this is of the form, am x minus 1 to the power m. Okay, so what is my am? Am is 1 by 3 to the power m. So my am plus 1 is 1 by 3 to the power m plus 1. So here r is equal to limit m tends to infinity am by am plus 1 magnitude. If I solve it, it's 3. Therefore r is equal to 3 here. In some book also, instead of r, the formula is also written like this: 1 by r is limit n tends to infinity an plus 1 by an magnitude. So don't be confused whether it is, if it is r, I write an by an plus 1. If it is 1 by r, so in some books it is also written like this. So don't be confused. The video is getting lengthy. We should conclude it here now. So to conclude, we have the second order or higher order non-linear differential equations, linear differential equations, and with the variable coefficient, basically not solvable by the earlier technique. We will use this power series method to solve it, but we should see that the power series solution must converge, but we are not bothered about the converge at this moment. It will go in this process. Okay, we will find the power series solution. So power series solution is an important tool that will overcome to solve the problem which is not solvable by the earlier technique, right? And once it is an infinite series, we must have a convergence, okay, for which we need the radius of convergence, and I discussed a few examples on this. So now, if at this stage my request to all of you is that if this lecture is useful to you and you feel that it is interesting, please like and subscribe to this channel, which will boost my motivation to upload subsequent lectures for your benefits. Okay, so thank you all. Have a nice day.